Sorry about that, guys. I was trying to mess with OBS. I'm not for sure if you guys know what OBS is or not. Trying to mess with it just so you could see my face a little bit, but for some reason it worked well one time, but then after that it kind of messed up. So that's why I was trying to fight that. But we should be good here. I see Tim, Morgan, Ian. We'll give a couple more minutes to the other people getting in here. There's Carter. Hey, let's start with number 24 homework. I'll just set this up here and we can kind of check our answers. And if you guys have any questions about it, we can talk through it. So I'll just set it there. We'll give everybody a couple minutes to get in due to my issues before we get going. But here is 1 through, there's 1 through 6. All right. Looks like Tim, Morgan, Ian, Carter are here. Some other people had messaged me about them not being here today. I appreciate you. I do appreciate you guys being in here. Any questions 1 through 6? Are there any questions 1 through 6? If you're good on 1 through 6, give me a thumbs up or something like that. One is -5. 2 is 22 over 3. 3 is 3. 4 is 2. 5 is 1. 6 is 2. Going down 7 and 8. 7 is 1/4. 8 is 0. 9 is 0. Any questions 7 through 8? Or excuse me, 7 through 9? Okay. Skipping down to 9 and 10, or 10 and 11, excuse me. 10 is -5/3, and 11 is 2. Okay, 9. Go back to 9. Go ahead, Morgan, with your question on 9. Okay, so let me grab a pen. So walking through 9. So we're wanting to know what is the limit of this function as x is going to negative infinity. So what is y doing while x is going to negative infinity? So first step would be to plug a very large number in here. And it'd have to be a negative large number. So just think about if you did negative 100 right here. So negative 100, or let's do something we can actually calculate. If you did negative, let's just do negative 5 here. Negative 5 squared is 25. So that would be 25 over, and then if you did e, you did that same 5. And it would actually be negative 5, so it would make that positive. And e to the 5th power is going to be some positive number, 148. So the higher those, like, so then if we go to 6, that would be 36 over something larger than 148. So I would have this number, the numerator's going to infinity, the denominator's going to infinity. Okay? So then from there, we have to say, all right, since that's infinity and infinity, we just take the derivative. So the derivative of x squared is 2x. The derivative of e to the negative x. Remember, you just multiply what this is times the derivative of the numerator, which is negative 1. So that's negative e to the negative x power. So again, use some number, like let's say negative 5 again. So if I put a negative 5 in here, I'm going to get negative 10. And if I put a negative 5 in here, I'm going to get 148, but it's going to be negative 148. So as those numbers increase, that numerator is going to increase, and that is going to increase as well. So that's taking me to negative infinity and negative infinity. So then my last thing I do is I take the derivative of that again. The derivative of 2x is 2. The derivative of negative e to the negative x. Well, negative 1, the derivative times this, negative times negative is a positive, and the exponent stays the same, e to the negative x. So then I type in something, can't type in something too big, but if I type in 2 over, let's say, e to the first, and e raised to the first power is 2.71, and 2 divided by 2.71 is going to be 0.7. As those numbers increase, as that number we put in there increase, if I did like 2 e to the second, that will give me 7.3. 7.3, 2 divided by 7.3, 0.27. So as you're seeing, the higher that number goes for x in the negative, going towards negative infinity, it's getting closer and closer to 0. Does that help, Morgan? Cool. Thank you. All right. And then let's go ahead and look at 10 as well. Carter, are you good on 9? I saw you said 9 as well. You good on 9, Carter? Okay. So going to number 10. Now, I think it would be valuable for you to understand that sine, especially since we're seeing as it approaches 0, sine of 0 is 0. Cosine of 0 is 1. And then therefore tangent of 0 will be 0. Okay. So I think it's important that you know those three, okay, in order to kind of flow with the rest of it. Okay, so here we go. Sine, if I we start all limits by plugging in. So if I plug in a 0 here, sine of basically 2 times 0 would be sine of 0, which is 0, minus 0, minus 0. So that's 0. And actually, I did that right here. And then plug a 0 in there. That's 0 over 0. Yeah. So then I take the derivative of that. The derivative of sine 2x, the derivative of sine is cosine, and the derivative of, and then you got to do the derivative of the inside, which is 2. So 2 cosine 2x, the angle stays the same. Minus the derivative of tangent x is secant squared x, and the derivative of negative x is negative 1. The derivative of x cubed is 3x squared. So now we plug 0 in here. So if I plug a 0 in here, cosine of 0 is 1. So 1 times 2 is that 2 in pink there, minus secant squared. And if you think, what is secant squared, or what is secant? Secant is the reciprocal of cosine, so that's 1 over 1 basically. So secant squared is 1, and then minus 1. So 2 minus 1 is 1. 1 minus 1 is 0. And then obviously 3, if you plug a 0 in there, you're going to get 0 there. So we have to take another derivative. So the derivative of cosine is negative sine. But then we have to take the derivative of this 2x again. The angle stays the same, but the derivative of 2x is 2. And then 2 times 2 is the 4 right there. Everybody still with me? Give me some kind of indication that you're with me on this right here. Give me just some that you're following. I don't want to just start spouting out stuff. Okay, cool. So then from there, we keep going, and we take the derivative of secant squared x. So think about moving that 2 to the outside and then doing the power rule. Bring it down. So that's negative 2. And then the derivative of secant would be secant squared tangent x. Secant squared x tangent x. And then all over 6x. So then again, knowing that sine of 0 is 0, sine of 2x is 0 times that, it's going to be 0. And then right here, I have negative 2 secant squared x. Now again, secant squared x is going to be 1 times that negative 2, but it's all multiplied by tangent x, and tangent x is 0. So 0 times any of this is going to give us 0. 0 minus 0 is 0. And then, of course, 6 times 0 is going to be 0 as well. Then we have to derive again. So we take the derivative of this. The derivative of sine is cosine, but each time we're multiplying the inside by 2. So negative 4 times 2 is negative 8. Then we move over here to negative 2 secant squared x times tangent x. And that's where we got to do product rule. So we take the first one, negative 2 secant, and actually I did this all on a piece of paper. This is where it gets a little bit crazy. Let me see if I still have that paper. And I do, lucky for you. Okay. So I have this right here, this negative 2 secant, this negative 2 secant squared x tangent x. I have it right here. Maybe a little bit hard to show on paper or on that with a little room. So we're having to figure out this right side of this using the paper right here. So again, I'm simplifying this using product rule. So I can just take -2 out to the side. Let me straighten it up for you guys. I can take -2 out to the side, right? And just do the first thing right here. So first, so -2 secant squared x times the derivative of the second. The derivative of tangent x is secant squared x. Okay, so again, the first times the derivative of the second, the derivative of tangent x is secant squared x, plus the second one, tangent x, times the derivative of this over here. And keep in mind here that if I just use that -2, if I pulled it to the outside and then just did the derivative of secant squared x, if I pull that 2, so yeah, look right here, actually. I did it right here. So secant x squared, pull the 2 down, times secant x, and then the derivative of secant x is secant x tangent x. So then that brought us to that. I actually said that I have too many secant x's in there. Sorry, that didn't make sense. So then it should just be 2 secant x, the inside, times the derivative of the inside, which would be tangent x. So 2 secant squared x times tangent x. And then we just multiply that -2 times the 2 and get -4 secant. No, that is right. I am right there. Sorry. That's where the squared is coming from. Sorry, it's been a while since I've done derivative of secant. So secant x, and then the derivative of secant x is secant x tangent x. And then you put both of those together to give me secant squared x times tangent x. Multiply 2 times -2. That gives me -4. Bring these two secant squareds together for -2 secant 4x, or secant 4 to the 4th x, and then just clean that up by -4 secant squared x tangent x. And then that takes us to this right here. Sorry, that get a little nasty in there. Anytime you're dealing with trig function, it can get a little nasty. All right, so then here, -2 secant to the 4th x minus 4 secant squared x tangent squared x. I just got that from the paper over here. So cosine of x is 1. So 1, or cosine of 2 times of 1, what is going, or cosine of, the cosine of 0, plug 0 in, and then 2 times 0, 0. Cosine of 0 is 1. 1 times -8 is -8. And then -2 times secant x, secant of 0 is going to be 1. So 1 times -2 is -2. Over here, again, that tangent squared x, if you plug that 0 into x there, it's going to make this whole thing 0. So then that leads you to -8 minus 2, which is -10 over 6, which simplifies to -5 over 3. That was a little sloppy by me. Sorry, I worked that last night at probably about 10 o'clock. So it's been a little bit since I've seen it. Questions on that? Give me a thumbs up if you're good. Okay. And then 11. We all good? Cool. All right, if you guys are good, I'm going to take this away, and then let's get out those notes. So let's go to number 25 notes. Okay, next to probably going back to our derivatives when we did that assignment where we did all derivatives with everything combined. That's a pretty important lesson in calculus. And number 25, indefinite integration, will be just as valuable as that. So I appreciate you guys being here today. This is a very, very valuable lesson for us as a calculus class. So this is a big part. Integrals are a big part of calculus. So once you have this out, give me a thumbs up that we're ready to go. Thumbs up. You guys are ready to go. All right. So in pre-calculus, you studied inverse functions. Also, in the review section of this manual, we have already spent time taking derivatives of inverses. The inverse operation is denoted f to the -1 or the inverse, not to be confused with x to the -1, the reciprocal of x. Remember that x is a noun while f refers to the process, which is a verb. Whenever we perform an operation and immediately perform its inverse, you end up exactly where you started. We say that the inverse of f of x is equal to x. And we say that f of the inverse of x is x. So below, write some mathematical operations and their inverse operations. So going back to our heydays, addition. So if you do the operation of addition, we know its inverse is subtraction. Okay. If you do multiplication, we know the inverse to be division. If you do square, you square something, we know the inverse is to square root. If you take the log of something, the inverse is just 10 to the x power. If you do trigonometry, it's just the inverse trig. And then if you raise to the nth power, we know it's just take the nth root. Very similar to squaring and square root. So if it's like to the 4th power, we take the 4th root. Since, give me a second to get that. Since differentiation of a function is a process, there must be an inverse to that process. So taking derivatives of a function, since it's a process, there must be an inverse to the process. There must be an opposite way. We call the inverse process anti-differentiation. For instance, we know that the derivative of y equals x cubed is 3x squared. We know that, the power rule. So it makes sense to say that an antiderivative of 3x squared is x cubed. However, it is important to say an antiderivative rather than the antiderivative of 3x squared for the following reason. As you can see by the figure to the right, for the following, the figure to the right, the derivative of x cubed is 3x squared, but so is the derivative of x cubed plus 1, x cubed minus 4, and x cubed plus 2 pi, as well as an infinite number of other functions. So again, if we were to do the inverse operation of taking a derivative, which we call anti-differentiation, obviously any of these could get us our answer to that 3x squared. All of this can take us to 3x squared, which could lead us to what we see now, this x cubed plus c. So, but when you go backwards from 3x squared, it is impossible to know from which function it originally came. So to cover all bets, we say that the antiderivative of 3x squared is x cubed plus c, where c represents a constant. I don't know if you have your highlighter, but you can underline that, something. It is important to attach the c after every antiderivative. That is a big deal. So basically, we're going to be taking antiderivatives today. And if you don't add a plus c after every one, it'll be wrong. You're saying that the antiderivative is not one specific function, but a family of functions. And that's why it's there's an infinite amount of them. There's an infinite amount of antiderivatives. So the process of taking antiderivatives is called integration. Specifically, indefinite integration because of the constant c. So we do not have to write the word antiderivative again. We use a symbol to represent the process. That symbol is called an integral sign, which is written like this right here. The way we write an integral is our symbol right here, the integral sign, the function, and dx. Okay? Now this dx is going to represent in what terms you're solving for. With what we're dealing with single variable calculus. When you go to multivariable or multivariable calculus, that's when this d of x is going to bring on some different importance. But pretty plainly, guys, this is just always going to be there, and we're solving in terms of x. You can kind of, and I think we address it later in the notes, but it's kind of very similar. Oh, yeah, it's right here, actually. The dx tells you the variable of importance when you are integrating, just as you write the derivative of y with respect to x. So the dx is just as important as you're saying this right here. And some of you guys remember when we were doing, I can't think of the name of it. Man, I can't think of it. Related rates. Sorry, it took me a second. Some of you guys remember with related rates, we solved stuff with respect to time. So we solved it in base of t, and that's when we kind of got into some different kind of problems. But for the most part, you're always going to see that dx there. Okay, that dx is going to basically be there. Another way you can think of this is to think of these as almost bookends. Okay, think of these as like, you know, if you had a bookshelf, think of these as like bookends. And basically everything between your integral sign and dx is what you're taking the antiderivative of. So they're always going to be there. They're always going to be on the end, and whatever's between them is what you need to basically do the antiderivative of. Okay, so since the derivative of 4x is equal to x, we will say that the integral of 4 dx is equal to 4x plus c. So because we know the derivative of 4x is 4, then that has to mean that the integral of 4 is 4x plus c, c being any constant. And since the derivative of sine x is equal to cosine x, we would say that the integral of cosine x is equal to sine x plus c. Remember, every antiderivative you're going to have a plus c on it. All right? And since the derivative of x squared plus 3x minus 1 with respect to x is equal to 2x plus 3, then therefore the integral of 2x plus 3 has to be equal to the polynomial x squared plus 3x plus c. Note that during the integral process, we don't get x squared plus 3x minus 1. The negative 1 is swallowed up by the constant c. Just as we have derivative rules, we have corresponding rules for integrals. And here are some basic rules. And we'll flip to the backside. So these are our differentiation of formulas, which we know. The derivative of a constant is 0. The derivative of kx is just k. And then you have a constant. You can always, if you have a constant times a function, factor out the constant and then take the derivative of the function, put the constant back in at the end. If you're adding or subtracting, just take the derivative of f of x and g of x. And then we know about the power rule as well. Same thing over here. If you have 0, we know that that is going to be equal to c. Any constant can give you 0. If you have the integral of k, it's going to be kx plus c. Same thing here with the constant rule. Same thing here with adding and subtracting. And then this right here is going to be probably the one you're going to use the most. And it's basically the power rule reversed. Instead of subtracting 1, we're going to add 1. And instead of multiplying by n, we're going to divide by n plus 1. The integration power rule is just as important as the power rule was to differentiation. It requires that expression be written with rational powers, so converting expressions to fractional exponents is vital. Converting expressions to fractional exponents is vital. Using this rule creates fractions, sometimes complex fractions. If you are not adept at working with complex fraction, check out the review at the end of the manual. We're all good with complex fractions. We can handle that. Okay? So now let's get started taking antiderivatives. Give me a thumbs up if you're kind of with me. Katie should be fine. Okay, cool. So, looking at number 1. Now, a couple different ways to think about this problem. Number 1's pretty simple. So, basically, it's saying what function, basically, what would I need to, if I got this as a result of a derivative, what would be the function that I got it from? Well, that should be pretty plain and simple. If you get 7, it comes from 7x. But then remember that we have to add what to every single antiderivative we take? Plus c. And that's it for that. Yeah, very good, Tim. Plus c. All right, for number 2, x, the integral of x to the 5th with respect to d of x. So, again, we're going to go to this, this power rule right here. All right, going to go to this power rule right here. So we're going to say x and then n, which would be 5 here. 5 plus 1 over 5 plus 1. So it should look something like this. X to the 5th plus 1 over 5 plus 1. That would lead us to x to the 6 over 6. And that right there would be my answer. Okay. So going to number 3, you're going to get into a pattern. You just add basically 1 to the numerator and then put that over in the denominator. X to the 13th over Oh, sorry guys. Yeah, always add plus c there. Sorry, look at me trying to tell you guys to always add c, and then I didn't add c. So x to the 6. Yeah, very good, Carter. X to the 6 over 6 plus c. Now coming over here, add 1 to the exponent, and then put that exponent over that, and then always say plus c. Now, just so we're all good in this, just so we're all kind of seeing this, let's take this x to the 6 over 6. Now, let's take the derivative of this just so you see, okay, this really does work. This power rule, we're doing the opposite of basically what we did with the power rule. So if I say low times the derivative of the high, which would be 6x to the 5th power, minus the high times the derivative of the low, which would be 0, over low, that takes care of itself. That is 36x to the 5th over 36. And then from there, the 36 cancel, leaving me just x to the 5th power. So just kind of showing you that this right here, when you do quotient rule with it, you're going to get, and do the derivative, you're going to get back to where we're at. Okay? All right, looking at number 4. So number 4 is x to the 4th minus x squared. Now, again, that would be my addition subtraction here, okay? And I just derived the left and the right. Show the work that I just did on the paper, Morgan. No, you don't have to do that at all. I just wanted to give you, hey, because sometimes you look at it as like, man, how in the world did that get back to x to the 12th? So, or x to the 5th. I was just trying to show you that, hey, this does work. So no, you don't have to do that work at all. Okay. So then coming right here, the integral of x to the 4th minus x squared d of x. So again, that's x to the 5th over 5 minus x cubed over 3. I cannot simplify any of that, so then I just say plus c. Okay. Jumping over here to 5, t cubed plus t plus 1. Same thing here. We can just take the derivative of each, or excuse me, the antiderivative of each. We can integrate them all. So t to the 4th over 4 plus, now think about that. That'd be t to the 1st there. So that would be t squared over 2. And then plus, don't forget this right here, t, the integral of a constant would just be that constant times x, so just basically 1t there. And then we'd have to add everything. We got to say plus c to everything. I cannot do any of that. I cannot really do anything there. So then I can't simplify is what I'm saying. Sorry. So then that would be my answer. Okay, looking at number 6. So the integral of 3x cubed dx. So now again, this is our constant rule, okay? So move that constant out and then take care of that, okay? So that would look like this. Move that constant out, and then I'm going to have x to the 4th over 4. Nothing simplifies there, so I say plus c. That's 6 of them. What do you guys think? Not too bad? Pretty simple, right? I'm not trying to like say, oh, get ready, wait for this. I'm not saying that at all. I'm just saying, what do you think so far? Any questions about this thus far before we move on? Yeah, pretty simple. Simple so far, yeah. Okay. What's up, Timmy? Or does that mean no questions or no like burn this whole thing? All right. So moving on to number 7. So number 7's the same way. You're just subtracting, so we can take each one. So we can say 4, or no, ooh, I about took the derivative of it. 2x cubed over 3 minus 7x squared over 2 minus 8x plus c. So this is what it's like to speak 2 languages, guys, because at 1 minute you want to take the derivative, but you're like, oh, no, I'm not taking the derivative. I'm taking the antiderivative. So it's kind of like both processes are going through your mind at the same time. All right. Let's jump over to number 8. So number 8. So we have 2/3 x to the 5th. Again, 2/3 is a constant, so I don't have to worry about that. But then I'll say x, add 1, x to the 6th, and then I have to put that all over 6. And then I say minus 7/3 is a constant, leave it by itself. X to the 4th over 4. Minus 1/4 x cubed all over 3. Now, just so we're all, just so we're making sure we're all good. 2/3 divided by, that's that complex fraction, 6 over 1. Guys, what you just need to do is just flip it up. So it's the reciprocal, so take this and flip it up. So put the 1 there, put the 6 there. 2/3 divided by 6 over 1. Actually, yeah, okay, yeah, cool. So that's 2 over 18 is equal to 1 over 9. And then don't forget that has your x to the 6 with it. So we're looking at x to the 6 over 9. So I can say this one is equal to x to the 6 over 9. Now go to the next one. The next one, 7 over 3 divided by 4 over 1. Just flip it up, guys, and get 7 over 12. And don't forget about your x to the 4th. And it is minus, so minus 7 over 12 x to the 4th. And then I do that last one. 1/4 divided by 3 over 1. Just flip it up. And that's 1/12. So minus 1/12. Or actually, I could say just x cubed over 12 since it's a 1. And then remember, everything has to have plus c. Questions on number 8. It's a little bit different. Had to just basically simplify here. Questions on 8. Seeing none, let's run over to 9. Okay. So here we go. Same thing here. E is a constant, guys. So just think about moving it to the side, and that's to the first power. So that would be e to the x squared all over 2. And then think about 1 over e. 1 over e is a constant. So I could just say 1 over ex, or just simply say plus x over e. And then always we have to add plus c. Again, just to make sure we're cool there, this is a constant, guys. So it's like saying just 1 over e x. So you could write it like that. Oh, sorry. You could write it like that. 1 over ex, but I just went ahead and multiplied x times 1 and put x over e. Not trying to confuse you there. So these two are the same. Okay. All right. Number 10. Moving right along. 1 over x squared. Now again, I highlighted this statement. It said we need to be able to convert expressions to fractional exponents. Okay. So someone type in the chat box, what is 1 over x squared as a fractional exponent? Come on, guys. This is not that bad. And when we say fractional exponent, yeah, there you go, Timmy. Good. Yeah, x to the negative 2. So we would say symbol, our integral symbol, x to the negative 2 of dx. So we basically just rewrote it. And then that would go to, again, you add 1 to the exponent. So negative 2 plus 1 would be x to the negative 1. And then we would put that over negative 1. The exponent and your denominator will be the same. And then if you think about, in order to simplify that, we don't want to leave negative exponents. So we would push it back down. So that would make, if we push it back down, we know our answer is going to be negative because they have a positive divided by negative. So a negative, that would push the x back to the bottom, leaving just 1 on the top. And then we say plus c. And that's what we're looking for. Okay, look at number 11. So I'm going to rewrite it. My integral sign, 2x to the negative third, and minus 5x to the negative fourth. And of course, that's dx. Okay. So then from there, take the antiderivative of that. So that would be the 2 is a constant, so it just chills out there. 2x to the negative 2 over negative 2 minus 5's chilling, x to the negative third all over negative 3. We can kind of clean those up just a little bit. The 2's cancel. And then to think about our final answer, guys, We don't want negative exponents, so push that x to the negative 2 down to get x squared in the bottom, leaving us just 1 on the top. And then think about this, and this would be a negative, negative, so we know it's going to be a plus there. And then thinking about this, we don't want to leave that as x to the negative third, so we want to push that down. So I should have on the bottom, the 3 remains, the negative is lost with that negative, and that's 3x cubed. And since I pushed the x to the negative 3 down, I'm just left with 5 on the top. And then that is plus c. I forgot my negative back here on this side. That would be that's still going to be a negative right here. So negative 1 over x squared plus 5 over 3x cubed plus c. Okay. Looking at number 12. So number 12, we know we would rewrite that as x to the 1/2 dx. So when we derive it, that would be x. Now I think I got to add 1 to that. Well, that's like saying 2 over 2 there. So 1 plus 2 is 3 over 2. And then that denominator has to be the same as that numerator. This is a complex fraction. There's a 1 here. So 1 divided by 3/2 would just be flipping this. So that would be equal to 2 over 3 x to the 3/2 plus c. Thumbs up if you're still with me. Hadn't asked you a question a little bit. Hadn't asked you a question since 10. Give me a thumbs up, smiley face. This ain't too bad, right? Okay. So jumping down to 13, I would rewrite 13 as 2y to the 1/3. Oh, sorry, guys. 2y to the 1/3 minus 4y to the 1/4. Dy. So again, we're just solving for y now instead of x. That's okay. So dy. All right. So then from there, we would have. Now we do the antiderivative. So we say the 2 is a constant, just it's fine by itself, and then add 1 to this. Well, that would be like saying plus 3 over 3. 1 is 3 over 3 with like denominators. So add 3 over 3 to that. And then that would be y to the 4/3 power all over 4/3. Again, 2 is a constant, so we can kind of take it out. And then y to the 1/3, add 1 to the power, and then that will be our denominator as well. And then we say minus 4 is going to be there. And then y to the, and then here we would have plus 4 over 4. And that would be 5 over 4 all over 5 over 4. So if we did some math here, you got 2 over 1 divided by 4 over 3. So just flip it up, guys. 3 over 4. And that equals 6 over 4, which is 3 over 2. So I have from here 3 over 2 y to the 4/3. And I could put that in the numerator with the 3 as well. I could put this right there with the numerator. Either way works. We're on the side. And then I have 4 over 1 divided by 5 over 4. And just flip it up. And that would be 16 over 5. So then that would be minus 16 over 5. And that's y to the 5/4. And don't forget about c. C represents that constant that can be anything. All right. Jump into 14. So we need to write that a little bit different. So I'm going to write it as the integral of, that would be, if you think that's 1 there, we flip, that's x to the 1/2, flip it up. That's x to the negative 1/2 minus x to the negative 2/3. Your index is always your denominator. What's inside is up here. The negative's coming by flipping it up. That with dx. So then I'm going to add 1 to both of those. That would be like saying plus 2 over 2 and saying plus 3 over 3. And that would take me to x to the 1/2. Negative 1 plus 2 is 1. X to the 1/2 minus x to the 1/3. And don't forget, sorry, I was getting a little carried away there. Make sure it has to be all over that denominator. Okay. So again, if that's 1, just think about this. It's just going to flip it up, guys. It's just going to flip up. So 1 divided by 1/2 is 2. So 2, and then I could say radical x minus that 3 flips up. And when I say flip up, I mean 1 over 1/3. And that's actually 1 over 1. It just flips up to where it's 3 over 1. Not trying to confuse you by what I say when I say flip up. Okay. So 2 radical x minus, and that would be 3. And then I could say the cube root of x. But don't forget about c. All right, 15. So looking at 15, same thing here. Let's just do what we've been taught. So I have, these are basically rational exponents here, so we really don't have to fight too much. Now we're solving it for x still, okay? So we're just doing the antiderivative for x, and it's saying n can't be negative 1/2. That'll make sense here in just a second. So I start with this one, x to the 2n, okay? X to the 2n would be x to the 2n plus 1 over, again, these have to be the same, 2n plus 1. Now, since we're solving this in terms of x, this n right here is just kind of like it's just kind of like a constant, okay? So, and then pi, we know pi is a constant, while this n is a constant as well. So the only thing we need to do to this is just add an x to it. So say plus n pi and then x. Now that should make some sense, because think about if we went the opposite way. So if I gave you this n radical pi x and I said take the derivative of that, you would say it's n radical pi. Okay, so that should make a little bit more sense there. And again, we're not solving for n in terms of n, we're solving in terms of x. So that's why we know n is just some constant. And we always remember to say plus c. And the reason that n cannot equal -1/2 is obviously because it would make the denominator 0. And folks, that's all I can do there. All right, tell me you're still with me. You're still with me, still hanging on. Any questions thus far? Give me smiley face, something. Yeah, not too bad. Okay. Assuming that I'm not seeing any questions, I will carry on. So let's go backside now. Okay. Morgan says go it. All right. So when you learned, this is actually pretty interesting here. When you learned inverse operations throughout your math career, the inverse function was always more difficult than the function itself. It was easier to learn addition than subtraction. It's easier to learn multiplication. Multiplication was far easier than division. You can always square a number, but taking a square root was difficult. So it is true with, it's the same way with differentiation and integration. You can always take the derivative of any function. That's pretty easy, pretty simple. But taking the integral is another matter. We will see that there are expressions that are not integrable. For instance, the integral e to the x squared power of dx cannot be taken. There's no expressions whose derivative is e raised to the x squared power. In taking integrals, you sometimes have to be clever. For now, there's a limited set of rules. There is no, for now, product or quotient rule of integration. If an integration problem cannot be written as a sum of expressions with rational powers, you may have to change the expression so that it does. And right here it calls this a bag of tricks. So, trick 1, you multiply out, then integrate. Trick 2, split into individual fractions, then integrate. Okay, so a couple of different things we can do here. But for instance, if we were to have something like this, yeah, 17 is perfect. So if I was to have 17, there is no like, oh, just do the quotient rule here. Low D high, high D low, over the low. But you can kind of split it up and do some different, you got to be clever with it. Break it up, split it up, do something like that. Okay, so let's look at number 16. So right here we have a binomial times a binomial. So the trick here would be trick 1, multiply it out and then integrate. So Carter, what is 2x minus 3 times 2x minus 3. No, just multiply it out. The FOIL, you remember you're the FOIL guy. So we're just foiling this. There we go. Okay, so 4x squared minus 12x plus 9 of dx. So obviously we knew the power rule in our instance right here would give us that if we were taking the derivative. But here, obviously, there's no kind of rule for it. So we just multiply everything out and then take the derivative. Or excuse me, we integrate. Okay, so from here, I'm going to say 4x, the 4 is a constant, 4x cubed over 3 minus 12x squared over 2 plus 9x plus c. Now I can simplify this right here. So I would say 4/3 x cubed minus 6x squared plus 9x plus c. All right, going to that next one, 17. Again, I don't have a quotient rule, so I just got to write each one of these over the denominator. X squared over x to the 4th plus 3x over x to the 4th plus 1 over x to the 4th. And all that's times dx. Or not times dx, but with respect to x. My dog is in there whimpering. He's just seeing all that sunlight out. He wants to get out, but we just gave him a bath yesterday, so that's just a bad combination because he just want to get out there and just slide around in the grass, get all nasty. But we let him do that every now and again. Please don't report me to whoever you would report me to. All right, so then integral. And then this right here, if we're thinking about this, so the x squared, yeah, there you go. Thanks, Timmy. The x squared right here, and then that would change that to 2. So if we're talking about simplifying this stuff, change that x and take off one of those, that would change that to 3. And then that can kind of be left alone. So I have really here, I have 1 over x cubed. Now, again, how do I write that as a exponent? X to the negative 2. And then that would be plus 3x to the negative 3. If I'm bringing that 3 up, it goes to a negative. And then likewise, plus x to the negative 4. Still haven't done any integration yet. Just trying to get it ready to do it. So now we're good here. So we would say x to the negative 1 over 1. Again, we add 1, or excuse me, that's going to be negative 1. Add 1, that's negative 1. So negative 1, negative 1. Plus the 3 is a constant, so it kind of stays. 3x to the negative 2 over negative 2. And then plus x to the -3 over -3. That will give me a final answer. Coming over here, push that x to the -1 down. So x is on the bottom, and it's going to be a negative. So negative, and then 1's left on top. -1 over x. That comes from that when I simplify it. That next one should just be -3 over 2, and the x squared, we don't leave negative exponents, so x squared, we push it to the bottom. And then here, x to the -3, that would be pushed to the bottom, so minus, because the negative right there, minus 1 over 3x to the third power. And then don't forget plus c. So this right here would be my answer. Okay. Number 18. Hey, I'll give you like a 3 or 4 minute break after 18. Okay, just to stretch your legs, whatever. All right. So number 18. Let's rewrite it. So integral, and then I'm going to write it as 6x squared over x to the 1/2 minus 11x over x to the 1/2 minus 10 over x to the 1/2 dx. So that's just trick 2, split them into different ones, and then we'll go from there. Okay. So then let's simplify here. That would cancel. If you take a half from 2, that's 3 halves then. So that would be 6x to the 3 halves. If I take a half from here, that would make that 1 a 1/2. And there I can't mess with that. Nothing to cancel. So then that leads me to 6x to the 3 over 2 minus 11x to the 1/2 minus 10x to the negative 1/2, because we have to lift that x up. All the rest of them are kind of taken care of. Okay. Now, I don't know how valuable it's going to be for, I'm going to write this really small though. Okay. So it's going to have to look like this. So I'm going to have to add 1 to every single one. So plus 2 over 2, plus 2 over 2, plus 2 over 2. They're all, the denominators are all 2. So I'm going to add 2 to each one. So I'm going to say 6x to the 5 over 2 over 5 over 2 minus 11 x to the 3 over 2 over 3 over 2, and then minus 10 x to the 1/2 over 1/2. From there, I just need to simplify all that, which is just the complex fraction portion of it. So simplify it all. So 6 over 1 over 5 over 2, just flip it up. 2 over 5, that's 12/5. So I'm going to write that up here. I'm going to write my final answer up here. 12x to the 5 to the 5/2 all over 5. That comes from this right here. So this, I ran out of space, so I'm coming up here. And then minus 11 over 1 over 3 over 2. Just flip that up. 2 over 3, that's 22 over 3. So 22x to the 3/2 over 3. And then lastly, negative, or it's going to be minus since it's a negative, 10 over 1 over 1 over 2. Flip it up, and we should see that that's 20. 20x to the 1/2. And that would be my final answer there. Give me a thumbs up. We feeling okay? Yes, Carter. Yes, yes, yes. Plus C. Everything's a plus C. Very good. Thank you, Carter. Or no, I'm sorry. That was Ian. Sorry. I thought that was, for some reason, I read Carter. Thanks, Ian. All right. Hey, guys. I'm going to give you to like 2:34. So just take a quick break, get it, use the restroom, drink, whatever, stretch, stand up, stretch your legs for a minute. And then we'll come back. Shouldn't be too much longer. Okay. Be back here at 2:34. So that's like 3 minutes from now. All right. Type something in the chat box. Let me know everyone's back, that you made it back, that you're here, you're listening. Ian's here. Cool. Thanks, Ian. Carter's back. Got you. Thanks for saying something. Yeah, sorry about that. So let me start all over. We took derivatives of trig functions earlier in the year, so naturally we should be able to go backwards and take integrals of expression involving trig functions. Differentiation and integration with sine and cosine function occur in calculus all the time, and students get confused with the signs. As a helpful hint, follow the alarm clock in clockwise direction to take a derivative, and counterclockwise direction to take integrals. So I always remember, like from what I can remember when I was in school, they would always say, and I saw this alarm clock then. They would always, I guess the sun's moving on me. Hold on just a second. Let me close this window. Okay. So anyway, when you're taking a derivative, taking derivatives is easier. Multiplication's easier. So it's like multiplication goes forward. Division is a little bit harder than integrals. So in division, you're going backwards. So counterclockwise backwards. Integral is a little bit harder than derivatives. And you just got to remember sine, cosine, negative cosine. We always start with sine, cosine, negative, negative. So easy way to kind of remember that. I got differentiation formulas and integration formulas here. All right. So let's get started in this. Number 19. The integral of 4 sine x. Okay, so the integral of 4 sine x. Well, if we're thinking here, sine, and we're going integral here. So if we're over here on the alarm clock, and this is really easy to draw, obviously. You go left, okay, and that's negative cosine. 4 is a constant, so that constant rule applies. So it would just be this. It would actually be 4, and then negative cosine of x. But we know that to be negative 4 cosine x. Negative 4. That's equal to negative 4 cosine x. Just moving the negative out front. And then always remember everything ends with plus c. Okay, looking at number 20. Negative 2/3 is a constant. I'm at cosine and I'm doing the integral. So if I'm over here on the alarm clock, I'm at cosine. And I'm doing an integral. So I'm going to go back to sine. I do counterclockwise, so go back to sine. Negative 2/3 is a constant, so it's just negative 2/3 sine of x plus c. Okay. Look at number 12. So 6 over cosine squared x. Now again, guys, there are no low-D high, high-D low, but we should know something about cosine and cosine. So this is, I could rewrite this problem like this. 6 over 1 times 1 over cosine squared x. I could rewrite that problem like that, and it doesn't change anything. But what is 1 over cosine squared x? 1 over cosine squared x is actually secant squared x. Okay, so it's actually, I'm going to actually rewrite the integral as this 6. So that's actually, this right here is equal to secant, obviously it would be secant squared x here. So then I would just say the integral of 6 secant squared x dx. So then that would be equal to 6, and these are just stuff you're going to have to know, guys, and you're going to have to study them. Secant squared x is tangent x. So 6 tangent x plus c. All right, look at number 22. So again, same rules apply here. 9 is a constant, so I just bring it out. 9. I'm at cosine, and I'm doing the integral, so I go counterclockwise, so that's sine x. And then negative 4, I'm at sine, and I'm going counterclockwise, so I go to negative cosine. So that would be negative 4 times negative cosine, which would be plus 4 cosine x. And then, of course, plus c. Can't do anything else. Okay, moving over here to number 23. Okay, so I have negative sine x over cosine squared x. Now, the cosine squared is actually a little bit of a, it's a little bit challenging just because we know that sine x over cosine x is tangent x, but sine x over cosine squared x is not tangent x. So I would have you rewrite this, okay? And I would have you rewrite the integral as this right here. One second. I'm so sorry, guys. My wife, I got a call that a student needs some help with my wife. Sorry. So I don't know where I was in that, but basically I can read, some of you probably followed along. Negative sine x, I can rewrite that as negative sine x over cosine x times 1 over cosine x. Because this is negative sine x over cosine x times cosine x. So I can basically split it up in order to simplify it a little bit better. Okay? So negative sine x over cosine x is negative tangent x, and 1 over cosine x is secant x. I have not integrated anything yet, so now at this point I integrate, and I just need to know this right here. Secant x times tangent x is secant x, and since that's a negative there, our answer is going to be negative secant x plus c. So this right here is coming from this right here. Just knowing that rule, that formula. All right, going over here to number 24. So number 24, we have 3 theta squared. So we're solving it in terms of theta here. So that, if we're going to integrate that, that's 3. And then I would say theta, and then raise that exponent by 1 and put that exponent over that. So that's just that simple power rule, or the inverse of power rule. And then minus, and then cosecant squared right here. Oh, sorry. Cosecant squared x is negative cotangent x. So negative, and that 2 is just a constant. So 2 cotangent x, or cotangent theta, same thing. And then that would go plus plus. My 3's would eliminate. So I'd have theta cubed plus 2 cotangent theta. And then we always have plus c. All right. Last page, guys. I think we just have 5 more problems. So thanks for hanging out with me. Thanks for staying with me. All right, let's go to the back. As long as there's no questions. Give me a smiley face. Let me know you're still with me. Shouldn't be here more than, hopefully this shouldn't take too long. So let me know you're here. Thanks for the enthusiasm, Morgan. So if we were given the statement f prime of x is equal to 4x, we can integrate each side of the equation to get the integral f prime of x is equal to the integral 4x dx. Okay? That leads to f of x plus a constant plus 2x squared plus c2, which is another constant. Since a constant minus a constant is another constant, we get f of x is equal to 2x squared plus c. So if we are given a statement, if we are given a derivative, we just integrate both sides. The left side is going to automatically be f of x, and then the right side is going to be your integration plus c. Okay? The original statement, f prime of x is equal to 4, is called differential equations, DEQs. In a differential equation, you are given a statement about a derivative of f prime of x. Your goal is to solve for f of x. So they're going to give you f prime of x is equal to something, and your goal is from there is to figure out what the f prime or what the f of x would be based on some stipulations. So because of the constant of an integration c, we end up with a general solution of a differential equation. if we are told in addition, so if we're told plus that if f of 0 is equal to 5, so if it gives us another kind of condition right here, this is called an initial condition, we can solve for C and will thus have a specific solution for that differential equation. All right. I don't really care for the way they write that out, but basically f of x is equal to 2x squared plus c, and then basically just solve for c there, and you get c equals 5, and then you just plug that 5 into the c, and this would be your original f of x equation. So that's what we're looking at doing here. It's not as weird as what it actually looks, I think. So solve the following differential equations with given initial conditions. So it's given us this right here, and this is our initial condition. So it's saying, hey, find your function that you come from this right here, and then find the more specific solution of f of x based on this fact right here about f of x, and that is when f is or when y is 2, x is 3. Okay. So we start by integrating both sides. So I have f prime of x d of x is equal to integral 3x minus 1 dx. So basically over here, the integral and the derivative cancel each other out, just leaving us f of x. And over here, we would just simply solve that the way we have solved all these today. So we would just say 3x squared over 2, and then just simply minus 1x. Just add an x to a constant. And then don't forget about plus c. All right. So then from there, we plug. So this is what we have. Can't simplify it anymore. So now I plug 2 in. So I say f of 2 is equal to, so plug 2 in there. 2 squared is 4. 4 times 3 is 12. 12 over 2 is 6. And then minus 1 times that 2, if we plug a 2 in, is 2. And then plus c. Okay. So once you get it simplified down to your f of x, now this right here is the general solution. This is the general solution. But once we get to this general solution, we then take the initial condition that the problem gave us, plug 2 in to see what we get here. And then from there, we're just going to set this right here equal and solve for c. 6 minus 2 plus c is equal to 3. So when f is 2, it is equal to 3. So since we need to solve for c here, we can just take what we found of f of 2, set it equal to what f of 2 is actually equal to, and then just solve for c. Okay, so then that would be 8 plus c is equal to 3. And then we subtract 8 from both sides. And hold on just a second. I'm getting something weird here. What did you say I did, Carter? It's minus, not plus? Oh, okay. My goodness. Okay, yeah. I was about to say, man, I keep seeing -1 over here, but then I was just like, that's not right. Okay, yeah. So minus, you can tell it's getting late. So that cancels, and C equals -1. I had that as my answer. I was just like, man, something's wrong here. So then here, once I find C, then I can go back and say f of x is equal to 3x squared over 2 minus x minus 1. And that's what I'm looking for. So it gives me the derivative in a condition from the function. From that, I can find the specific solution for the function without a C. Okay. Looking at 26. So 26, same thing. I'm going to do the integral of this side. So f prime of x is equal to the integral of the other side. And that would be x squared minus 2x plus 2 dx. So we know on this side we get f of x is equal to, and then we integrate this side right here. So that would be x cubed over 3 minus 2x squared over 2 plus 2x. And then obviously from there we'd have our plus c. Before we plug in our 3 here, we want to simplify that. So that's just f of x is equal to x cubed over 3, and then the 2's would cancel, minus x squared plus 2x plus c. So that's our function here. That's our what we would call our general solution. But given the stipulation that f of 3 is equal to -1, we plug 3 in. F of 3 is equal to 3 squared is 27. 27 over 3 is 9 minus 3 squared, which is 9, plus 6 plus c. So this is f of 3. So we set this. We know that's going to cancel. So we just basically set that equal to what we have here. So 6 plus c is equal to, this is what f of 3 is of the function. And we just set it to what that is equal to, -1. In order to find our c, we subtract 6 from both sides. Let me see if I can do a little bit better job this time. And c is equal to -7. So then I rewrite my final function. This is the specific solution given this condition. And that's f of x is equal to x cubed over 3 minus x squared plus 2x minus 7. Now, I have this typed in to my calculator right here. I have this function right here typed in. X cubed over 3 minus x squared plus 2x minus 7. So when I graph that, I can graph it. I get the graph. But really what I'm wanting to just be sure of, they did say in this, the f of 3 is equal to -1 here. F of 3 is equal to -1. So if I just went to the table here and found 3, I would be at -1. So that just kind of reassures that I kind of have the right function. All right, looking at 27. Okay, so 27 presents something a little bit different. So it says f prime of x is equal to 2, f prime of 4 is equal to 0, and f of 4 is equal to 1. So it wants us to find the final function given all these guidelines right here. All right. So here's what I know. If f prime, okay, of x is equal to 2, So then that would mean that f prime of x is equal to the integral of that. The integral of 2 dx. Remember, these are just the kind of like bookends to hold this in. And so when I then do the integral of that, f prime of x would then be actually 2. When it's a constant, just add x to it. But then don't forget about plus c. And since I'm dealing with possibly more than one c here, because this is f prime of x, I normally went from f prime to f of x. So I'm going to say 2x plus c1 because I'm going to have more than one c here. You'll understand here in a second. So then I look at my guideline for f prime of 4. So f prime of 4, I plug that into that x. 4 times 2 is 8 plus c sub 1. Now remember what we did here. We plugged that, we set that equal to whatever the f prime of 4 was. So 0. So I say 8 plus c sub 1 is equal to 0. And c sub 1 is equal to negative 8. So what that does is that gives me my derivative. F prime of x is equal to 2x minus 8. So this is basically this is just an extra step compared to these. Here it didn't give me the derivative, it gave me the double derivative or the second derivative. And then from there I got to find the derivative and now just work what I did over here and say f of x. Of course I could do my intervals here, you know. F of x is, or my integrals here, but f of x is equal to the integral. I will use it over here. 2x minus 8 dx on the outside. So then I get f of x is equal to, that would be 2x squared over 2, and then minus 8x, and then plus, and we'll just call that C2. So these two aren't going to make a difference. I just didn't want C to be on the same problem. From there, that cancels. I have f of x is equal to x squared minus 8x plus c sub 2. Then I have f of 4. And f of 4 would be 16 minus 32. 4 times 8 is 32. 4 squared is 16. Plus c sub 2. I set that all equal to whatever that 4, that f of 4 equals, which is negative 1. If this right here is f of 4, then set that equal to negative 1. 16 minus 32 plus c sub 2 equals negative 1. 16 minus 32 is negative 16. So then add 16 to both sides, and you should get C2 is equal to 15. That gives me, I line that back up with this right here, and gives me my f of x is x squared minus 8x plus 15. Give me thumbs up if you're kind of following this differential equations. Okay. Number 28 then. So f prime of x is equal to 2x. So in order to find f prime of x, that's going to be equal to the integral of 2x dx. So then f prime of x would then actually be x squared. And then plus c, and I'm just going to call that c sub 1. And just so I kind of skipped a step there, but obviously that's a constant, add 1 over 2. So that's where I was kind of canceling those two. Sorry about that. So x squared plus c. So then I say f prime of -3 here, because that's what my f prime is. That's the condition there. So f prime of -3 is equal to, plug in a -3 there. -3 squared is 9 plus c sub 1. I then set that equal. This is what f prime of 3 is equal to. So set it equal to 0 to find c. So 9 plus c sub 1 is equal to 0. And c sub 1 is then therefore equal to -9. So my derivative of this is equal to x squared minus 9. Then we just bring that over here and say f of x is equal to the integral of x squared minus 9 dx. F of x is equal to, that would be x cubed over 3 minus, it's a constant, just add an x, and then don't forget your c. We'll call it c2. I can't simplify anything, so now I'll just plug in what it gave me, f of -3. So I figure out what that is. That's 27 over, or actually -27 over 3, which would be -9. And then -9 times -3 would be positive 27 plus c sub 2. -9 plus 27 would be 18 plus c sub 2. I set that equal to 10. I subtract 18, and I get c2 to be -8. So my function, my f of x, would be equal to x cubed over 3 minus 9x minus 8. Last problem, guys. Hooray, hooray, hooray. When we used to throw the last bale of hay, we used to go crazy. Everybody would scream last bale. So this last problem, we get excited. All right, so here we go. Given that the graph of f of x passes through the point 0 pi, and that the slope of the tangent line to f at the point x comma f of x is 1 minus sine x, find f of pi. All right. So I think the key words in this is this: the slope of the tangent line to f at the point this is 1 minus sine x. So what that is telling me is this: the slope of the tangent line to f. And again, the slope, thing about slope of the tangent line. So basically it's telling us our tangent line is this right here. So f prime of x is equal to 1 minus sine x. Okay. So then from there, I just do the integral of both sides. From here, I'd get just f of x is equal to 1 would be x, and then sine. And think with integrals, you go, and again, this is where that clock comes in. Sine X, cosine X, negative sine X, negative cosine X. Think counterclockwise. So negative sine X would take us back to cosine X. So plus cosine X. And then obviously that's all I have there. And then I say just plus C. I then find f of 0 because that's it gave me that point. So it's telling me the function f of x passes through 0. So f of 0 is equal to 0 plus cosine of 0 would be 1 plus c. Now I take this 0 plus 1 plus c and set it equal to what f of 0 is, and that is pi. So then I find c to be equal to pi minus 1. So that gives me my function f of x is equal to, back over here, x plus cosine x plus pi minus 1. And then the question is literally saying find f of pi. So f of pi is equal to pi plus cosine pi plus pi minus 1. Cosine pi is 180 degrees. So what is our x coordinate at that? Excuse me, not x coordinate. Y. Did I say that right? Yeah, negative 1. Right. I did say that right. So that should be f of pi is equal to, negative 1. So negative 1 there, right? So negative 1 minus 1 would be negative 2, and pi, that's 2 pi. Since we're adding those, 2 pi and then minus 2. Guys, that is integrals. What do we think about it? Talk to me. I don't want to keep you much longer, but just tell me how you feel about integrals. Not that bad, Carter. Okay, cool. Somebody else, your thoughts? Yeah, for sure. Yeah, you'll get plenty of practice with this homework, Timmy. Absolutely. So this is that other big part, guys, of calculus. And Ian, I think it was you. Ian, I think it was you that told me like you had a friend somewhere and they started doing, integrals a little bit later, antiderivatives. I can't remember what you told me, that a lot of people may try to teach this right after derivatives, but that's what I like about this curriculum is that there's so much that you can do with derivatives that I like the way this is laid out. You knock out derivatives first, and then you apply derivatives in everything that we've applied derivatives to. And then you go to integrals, which is antiderivative, which is obviously the antiderivative here. So basically the same thing. We're just working backwards now. So we go forward, and then we go forward, and then now we're coming back. Okay. I appreciate your guys' patience today. I know we went over 2 hours, but I do appreciate you guys hanging on with me and being here. I hope I answered all your questions. I hope this is working well for you guys. Fortunately for you, we only had class 2 times this week, so I can justify a 2-hour lecture because of that. But then I don't see you guys until Monday. So Monday is when 25 homework will be due. Actually, let me look at the schedule right now. I need to see the schedule just to kind of tell you what time. I think we're fine at 1 o'clock still. Let me look at this schedule real quick, and I'll send this out to you as well. Yes. Actually, hold on. Yes. Mm, actually, I have you guys for completing 25 homework and then doing 26 notes. We're just going to meet twice next week. So is Tuesday. What would you all? I'll just ask you guys in here. What would you rather do? Meet on Monday and Wednesday, or Tuesday and Thursday? I'm pretty flexible next week just because my other classes are pretty they're a little bit flexible next week. It's the week before spring break. Okay, yeah. So everyone's saying Tuesday and Thursday. Okay. So I'll send out the schedule, but number 25 homework. So on Tuesday, we go over number 25 homework and do number 26 notes. Does that sound good? I love how you all said the same exact thing. Were you on a group text saying, was one person on there saying, hey, go Tuesday, Thursday? You all it came up kind of fast. So, hey, you all hey, don't scrouch on this. I know you're going to wait till probably Tuesday morning, but do it on Monday night. Okay. Do it on Monday night. Y'all do a group FaceTime, Timmy, and you don't throw me into the FaceTime, Timmy. Thanks a lot, man. Hey, that's all I have today. Thank you guys so much for sticking around, and I'll see you guys on Tuesday. Be careful. Have a good weekend. You guys are dismissed. See you guys. Have a good day. If you have any questions, feel free to reach out to me, Canvas, or you can email me, or you can tell me something, or you can ask me right now. I just wanna run me, run me.